Hi, everyone. I'd like to talk about some work I did at University of Pennsylvania, looking at associations between neighborhood socioeconomic status and functional brain network development, but it looks like I don't have slides at the moment. You can just give the talk off the top of my head. I've been told that they're working on getting slides up currently. Great, thanks so much. So just to recapitulate what I just told you, I'm going to be talking about neighborhood socioeconomic status, or SES, as I'm going to refer to it in this talk, and functional brain network development. So recently there's been emerging interest in how early environments affect brain development. And a bevy of recent studies have found that SES, socioeconomic status, has effects on both brain structure and brain function during task and rest. In the past couple of years, a couple studies have suggested that exposure to an under-resourced or low SES environment might result in accelerated structural brain development. However, functional brain development has not been as well examined. And so if we were to see the same pattern of results on functional brain development as we see on structural brain development, we might expect to see something like this, where the high SES kids in orange show a more protracted trajectory or a weaker association between age and some metric than the low SES youth, which are shown in blue. Which show a more accelerated or stronger association. However, studies thus far have mostly been restricted to seed-based approaches, which pick one area of the brain to look at, and no one thus far has addressed this with a data-driven network approach. Since SES represents broad environmental and lifestyle variation, we might expect to see effects of SES on a broad and distributed set of brain regions. So the goals of this particular work were to look at changes in large-scale topological properties of resting state brain networks during development, and to examine the effect of SES on these associations between age and brain networks. So to do this, we'll take an explicitly hierarchical approach. We'll start at the average whole brain level, then drill down to the system level and look regionally as well. To do this, we leveraged a large developmental data set, the Philadelphia Neurodevelopmental Cohort from the United States, collected by Ted Satterthwaite and some of his collaborators, that all had resting state and structural scans. They also had information on their neighborhood SES, which was derived from geocoded census block data. This was a factor published on by Tyler Moore in 2016. So Philadelphia has one of the highest rates of child poverty in the United States, and there is a vast difference between a low SES neighborhood in Philadelphia and a high SES neighborhood in Philadelphia in terms of the percent of people in poverty, the median family income, crime, dilapidation, and such. All our analyses also controlled for these covariates, so sex, race, motion, and average weight. Just to give you a quick overview of how we constructed the networks we're going to look at here, we use the multimodal cortical Glasser parcellation, which Dr. Glasser talked about on Sunday, which has 360 cortical regions, from which we extracted residual time series after preprocessing and correlated each of these 360 regions in the brain with each of the other 359 regions in the brain, resulting in this 360 by 360 adjacency matrix you see in the bottom right. So here the red is positive Pearson correlations between regions, and the blue is negative weights, so negative Pearson correlations between regions. One of the novel features of this approach is that we were able to use all the information in this network, so we didn't binarize or threshold this network using both the negative and weakly positive weights. And from this, we can construct a representation of a given subject's functional brain network. Once we had these brain networks, we chose to examine a measure of segregation, specifically local segregation, called the clustering coefficient, so C here, where you can see the node in blue has a high clustering coefficient, the node in green has a low clustering coefficient. This essentially reflects the prevalence of clustered connectivity around a node, or the number of a node's neighbors who are also neighbors of each other. So in a binary network, it's operationalized as the number of triangles as a proportion of the number of possible triangles around a node. But I would note these are weighted networks, so we used a generalization specific to this. So what we first wanted to do was look at what segregation looks like with age. So how is functional brain network segregation associated with age? And what we found, replicating prior work, is that segregation is positively associated with age. So I would note this is a cross-sectional sample, so we can't speak to developmental trajectories, but this is consistent with both prior work in this data set, which was Dr. Satterthwaite talked about yesterday, and work in other data sets of a similar age range. This likely reflects the increasing refinement of network architecture as kids grow up. But we wanted to drill down a little bit and ask, in what areas of the brain is this most strongly the case? And so we used the Yao 7 networks and assigned each of the nodes that we were examining to one of the 7 networks to see in which networks was this effect of age on segregation the strongest. And what we found is that segregation is increasing across the brain, but most strongly so in the attention and default mode networks, which are networks that we know undergo maturational processes during late childhood and adolescence. But what we were really interested in is the effect of socioeconomic status, SES, on these associations with age. So how does SES relate to brain network topology? And so here I'm plotting a median split of SES into low and high, but the results hold when you look at SES continually. This is easier for visualization. You see high SES in orange and low SES youth in blue. And what we see here is that high SES youth show a stronger association between age and segregation than low SES youth in blue. And so this is, just to jog your memory, the opposite of what we might expect with the acceleration hypothesis I showed earlier for structural brain development. This is consistent with an interpretation of faster functional brain development in high SES youth, although I note again that we can't speak to that because of the cross-sectional nature of the sample. So again, we wanted to ask in which areas was this most strongly the case. So where does SES most moderate age-related increases in local segregation? And we found that this is true most strongly in the limbic and somatomotor systems, although this is also true in other systems. And the limbic system in particular has been shown by many other groups to be sensitive to experiences of adversity early in development. And we find, in accordance with their findings, that prefrontal areas of the limbic system are sensitive to experiences of adversity early in development. Here, we're looking at neighborhood SES, which is a distinct but potentially overlapping construct with adversity. The somatomotor system was a little bit surprising to us. So there's been work showing that effects of SES are visible on somatomotor systems as early as infancy. This is a 2015 paper from Gao, the infant group that was cited a lot in the previous talk. And we hypothesized that potentially we are optimized to detect effects of the environment on early developing systems that undergo earlier maturation, such as the somatomotor system. Finally, we wanted to drill down a little bit farther and look regionally at which regions were driving this effect. So here I'm plotting the age by SES interaction with the areas that are significant after FDR correction shown in red. Yes, that's red. And we can see this recapitulates to some extent the system level effects. So we see this somatomotor strip as well as the paracentral lobule. There's some areas of orbital frontal cortex that are a little difficult to see at this angle. And if you plot the double-dipped interaction effect from only the significant regions, you can see it's really the strong association between age and segregation in the high SES kids that's driving this effect. Finally, we sought to ask whether this effect was distance dependent, so whether it was spatially embedded. There's been much ado about long distance connections being important in development, but there's also a body of work in network science that suggests that brain networks involve a trade-off between the wiring cost of anatomical connections and the emergence of adaptive topological properties for information processing. And we thought this trade-off might be shifted by the metabolic constraints that might be associated with the environment. So here what I'm plotting is the strength of the interaction effect across subgraphs composed of edges of different lengths, from the shortest on the right to the longest on the left. And what you'll see here is that it's, to some extent, the short-range connections that do show this age by SES interaction effect, but it's really not the long-range connections. So in gray is a permutation-based null model for each of these subgraphs, and we find that it's really the middling length connections that show the strongest age by SES interaction effect. And we did many supplementary analyses, but in one of them, we looked at which regions were edges between which regions were actually driving this effect, and it turns out that it is the edges between these regions in red that I show here. So in conclusion, we found that segregation is positively associated with age in late childhood and adolescence, and that SES moderates this association, most strongly so in the limbic, somatomotor, and ventral attention systems. This was partially explained by spatially distributed circuitry indicated by middling link connections. And I think this provides some hope, since neighborhood SES might be more amenable to intervention than things like household SES, parental education, or income, although people are working on changing parental income. But I think the really burning question here is, what specific aspects of this broad and general construct contribute to the associations that we see with brain development? So future work should work to disentangle the contributions of specific aspects of both the home and neighborhood environment, which will require more detailed data on both of these. So I'd like to thank my mentors and my funding sources, and invite you all to come to the poster this afternoon, ask me more questions there, or check out our paper.